Welcome back everyone. So, we are studying NPTEL course Topological Phases of Matter, and we have learned the mathematical foundations of topology, and then we have shown how topology arises in the presence of magnetic field, mainly in 2D, and we talked about Aharonov-Bohm phase, chiral phase, flux quantization and magnetic monopole. Then we talked about quantum Hall effect, charge pumping due to flux quantizations, and then we studied that problem in a lattice, and during that we also showed that when we study the Landau level problem in a lattice, we get band structure associated with corresponding to each Landau levels, and we made a heuristic argument that those bands will have a Chern number, and we showed it quickly using Kubo formula how that appears. And now we will formalize this definition of topology without magnetic field. And so, the first thing we learn is Beery phase, and also it is called geometric phase. So, there will be a lot of characteristic similarity of this Beery phase with the chiral phase and parallel transport, but the point to emphasize here is that these things will just appear without any magnetic field. So, that is more of a geometrical effect. Okay. And then we will talk about topological invariants. So, first we will do the formal derivation in two ways. One is very similar to what we did in chapter 1, and then we will do a more quantum mechanical version of it starting from Schrodinger's equation. And then we will move on to momentum space through block states and how to write the Beery phase in terms of the block state and also in terms of Hamiltonian, and how that would relate it to the Kubo formula. Then we will talk about various topological invariants in 1 dimensions called winding number, 2 dimensions called Chern number, and then we will generalize those to higher dimension. Okay. And finally, we learn how Beery phase arises due to band inversion and vice versa, and what that means, and also what that would correspond to a gauge obstruction to the block state in a Brillouin zone. So, formal definition of Beery phase derivation. So, let us do the way where we learned from parallel transport. Okay. And so, here we are studying we have some Schrodinger's equation for time dependent and time independent, and there is a state and there is a Hamiltonian that gives you the time dependence of the time evolutions of the state. I think just general state and time independent Schrodinger's equation. Alright, so this is a equation of motion, and we sort of alluded little bit when we talked about the directional derivative, and directional derivative is done for on a function, and then we generalize that to covariant derivative when we are doing the derivative on the fiber, and we are on a fiber now. And so the directional derivative or covariant derivative was the total change of the state and then on a curve, and then we had a term which was the tangent vector and plus the partial derivative in the time domain, right. And then we said that the parallel transport, the idea of parallel transport is to make the total derivative to be 0, right, so that the state remains always parallel, and that gives rise to all the equation of state we alluded that time, and here we are actually going to see that and we are going to use that. So Schrodinger's equation is nothing but a total derivative of some state okay, and that is nothing but and we do these things on chart and minus or plus. So here you can choose, okay, and we said that this is the term that gives rise to the Poincare bracket in classical mechanics or Heisenberg term in the quantum mechanics and so on, and this one is related to H. So I am writing the final result and you will see that it is just a matter of some normalization. So this term came from here and we just added this term, so it is just for our convenience, minus this which is from this term, and we want this to be 0. So this is our covariant derivative, right. And we want this to be 0, and that gives us the Schrodinger's equations I was writing. Okay, and if we solve it, we will get, and if we solve it, we will get the parallel transport, which is only e to the power I 1 by h dt psi t0 to t psi t0. Okay. So this is kind of our parallel transport. But this is the dynamical phase that we have already know. Right. So where is the geometric phase? Where is the Beery phase? So the Beery phase is hidden here. What we have done is that we have just treated it as this one is acting on some function. We really have not taken it as a fiber. What to do if it is a fiber? We just have to generalize this with a connection. right. And whether a connection exists or not, that we will see, the system will tell us. In fact, this Hamiltonian will dictate if there will be any connection. And also that this is a frame, this is a fiber, so that means there has to be a frame, and what sort of frame we choose. Generally we are looking for some energy eigenstate and which is an index, but then there are orbital states in which the Hamiltonian was originally written, which has non-off diagonal term, and then we diagonalized it and got to a diagonal Hamiltonian, with this being the energy eigenstates. So, in the original basis, orbital basis, they were, when we write these states in terms of orbital basis, so we are sort of expanding each eigenstates in that orbital basis, and those orbital bases are the frames, and how they are rotating as we time evolve the system is how a Beery phase will arise in a given band. For dimensional reason, there will be a h bar and a plus sign is assigned. Okay. So, if we do that, then what will happen is we will have a covariant derivative minus well, we can write anywhere. So, let me go back to H and minus H A. Okay. In fact, I have not even defined a chart, so we will just keep it this way. And then if we solve it, we will get this. I still have not explained where does this term come from, which I will do in a different way, but this is what we learned in chapter 1, that this is a valid way of doing it, and we also have learned what this one does. It just takes care of how these states, let us even take the energy eigenstate, so that just makes it easier for us to understand, but otherwise general state is also fine. And these states are sort of expanded in some orbital basis, and how it is rotating in the orbital basis is what is take care of it. But then you do not want this to be rotated, so you put a parallel transport. And if you solve it, you will get okay. In fact, when we bring I to this side, we have a minus, and that minus sign is also there in the previous one. Because we brought this I to the other side. Okay. So, this is still the dynamical phase, and this is the Beery phase, the exponent is the dynamical phase. And we are interested in the dynamical phase. So, let us just assume that the dynamic, so we are interested in the Beery phase. Let us just assume that the dynamical phase is just a simple trivial term. We can even set the energy eigenvalue to be 0 for the time being, and nothing changes. You can again put it back later, and what that would do is that then we can define is in a chart. So, we will have del mu, or even I think we don't need it in a chart. Since these states are all orthonormalized, so which is from here. So, we just set this one to be h is to be 0 and this entire covariant derivative is supposed to be 0, which gave us this solution, and now we put h equal to 0 also for simplicity. So, what we get is A is equal to I psi n del t psi n. And this is Beery connection, and Beery phase is then. So, generally one writes it as gamma, and do not be confused with the curve, the gamma we used for curved in first chapter. So, from now onwards we will use it as gamma will be as a Beery phase. Okay. And right, and here the index n, which I will try to use in the superscript for a reason that will be clear later. Okay, it is for a given band. Okay. This is formal but not so intuitive. So, let us do the rederivations. Derive it from Schrodinger's equation. This will be much more systematic and formal, and we will get better understanding of where does it come from. Okay. So, let us say, so our starting point here is some general state, and then we assume that there are n orbitals. When you said orbital, we meant any basis in which the Hamiltonian is written. Okay. In orbitals, or let us put capital N, and so that you will have this index 1 to n. Okay. Which means we can expand this psi So, these are our orbital bases. Of course, when you said orbital, it can be orbital itself, sublattice, spin. In some cases, we also have other bases, kind of valley and all, but any general basis, right? Or let us put it equation 1 and equation 2. So, now doing this, putting 2 in 1, we get So, this is the derivative of the state vector. So, that is like the change of the frame that we talked about, is equal to H okay. So, and then what we will do is that, so n states are all orthogonal, these n states are orthogonal. So, which means we can just multiply from left side by m, and I have not yet specified whether they are instantaneous or not, but it is sort of obvious that they are instantaneous states. So, there can be a time dependent. So, multiply m state from left. So, which means I am multiplying m, and this is just a number, this will go out, and then also this will be a m, and also this will be m. So, then obviously n and m okay. So, you can only choose the m state, that will give us high m, and we can write the remaining ones. Will then be equal to and the right hand side, which will get a IH cross so I have already taken to, so I have taken it to, so this is the term which you wrote, I have taken it to this side, so I will get a negative sign with IH cross and alright. Alright. So, now what we choose is an adiabatic approximations. Slight digression. So, roughly speaking, adiabatic approximation is when the time evolution is very slow compared to the energy gap modulo the h bar, then the time evolution is so slow that almost at every time there is an instantaneous eigenstate and eigenvalue that one can solve even for a time dependent Hamiltonian, right. So, these are the instantaneous states and instantaneous energy eigenvalues. So, the second point of this is that as the system evolves in time, at a later time the energy eigenvalues are like this. So, it has sort of moved from here to there, there to there, but it's so slow and the gaps are so large that there has not been any label crossing between these two states or any of these states. So, if it was n equal to 1, n equal to 2, it remains n equal to 1, n equal to 2. So, n equal to 1 state has not become n equal to 2 and vice versa. So, the quantum number of each state remains corresponding to a given eigenvalue, the quantum number of the state remains the same. Okay? And that is what we will assume here, that there has not been any transition from n equal to 1 to n equal to 2 or any n to m state in this transition. So, there has not been any level crossing. Okay. So, if that is the case, then we can use equation 5, this instant eigenvalue equation, and it will be easy to show that. So, this is the second term from here in which we have used this. So, e to the power n will come out and they are normalized. So, we will only have mth term that will survive, and this is the term I am writing, the second, which will give us okay. So, the second point about adiabatic approximations I meant is mathematically means there is no level inversion equal to 0 if m not equal to n. So, it has changed, but it still maintains its eigenvalue such that this state still remains orthogonal to any other state except n equal to m. There it does not vanish. So, we can then use this fact, and what we will get is, and so we only have then so I think I have missed out this factor. Right. So, this factor I missed out. So, okay. So, you can just divide everything by psi m. So, this is also then equal to so if we divide psi m, I will have this term goes away, this term goes away, and then you can solve this and we will get the first term will just be a dynamical phase, and the second term will be generally we set this to be 0. Okay. Again, this is the dynamical phase, this is the Beery phase, and okay. So recall that we put a H bar on the Beery connection earlier, and the reason now is obvious that we wanted to get rid of the H bar which was here from here, and this is the term in fact this is an important point. There is no I here. There is an I here, there is no I here, so this I comes here, but this I drops out from here, and H bar also drops out. So in fact all right. So you got the Beery phase is equal to I 0 to T n dot dt. So let me make this connection. So it's how much the state of the frame has changed, then we expanded into the original frame is how it was defined also, right. So this was the term that we defined as connection. For the nth state. Okay. On a chart, so I had some abstract manifold, and in which this Schrödinger's equation was defined, and H is also just an abstract one, we have not defined with in terms of special variable, but then we are locally had some manifold and we are going to a RD with some homeomorphism. So if you do that with some chain rule, one can then write it easily that del mu n dx mu, and this will be our Beery connection, the nth band for a nth band for a derivative along the x direction or muth direction. Okay, this is the Beery connection. On a loop, then on some manifold we have some base point and we do some loop, So generally Beery phase is a well defined quantity only on a loop. And if it's on a loop, and then we can sort of, and there is a summation over mu is implicit. So it's actually a dot product. Right. And then we also can define, if it's at least 2 dimensions, so we can define a surface enclosed by this. And this is the curvature. On the nth band. Okay. And that component wise, let me remind you, okay. So the question is not, so one thing which is not clear here is that this term then has to be purely imaginary to qualify for this to be a phase. Otherwise, if it has a if it's not a pure phase, then it will change the amplitude of the state, which is not allowed, because it's supposed to be only a parallel transport. It should not change the amplitude, and for this to happen, this has to be purely imaginary, and for this to happen, your Beery connection has to be purely real, and that we can show very easily, and I will put it as a homework. Show Beery connection is real. Okay. So then we will do a quick thing in terms of Beery phase in terms of Hamiltonian, or how the Hamiltonian enters into getting a Beery phase. Hamiltonian is much more intuitive. We can parameterize in terms of tight binding parameters, and with block phase in terms of sine k and cosine k. So it's much more intuitive to see what sort of Hamiltonian will correspond to a Beery phase. Okay. So bulk of this derivation I will leave it for homework, but I will guide you to how to do this derivation. Okay. So from this expression, if you write explicitly, what we find is that, and so because this guy has to be purely imaginary, as we talked about, and so you can even write it as just the imaginary part of this Beery curvature f, and f is connection times ds, some surface integral, and we still have not specified whether it is momentum of space or real space, which means this actually works for anything. Okay, so you write it in terms of f Levici beta or any other way, okay, and summation symbol is involved, and then you play with these parameters. So, this one is also in del mu, the muth component will be in, and if you do all this, you will get an answer that will be cross product, because it is an antisymmetric product, and this antisymmetry will translate into cross product. Just taking the derivative on both sides. So, there is one derivative on the connection, and connection also had another derivative. So, these two derivative you can separate into one on the bra state, another on the K state. So, this is a simple homework for you to do. Okay. And then, so then this is my Beery curvature. So, then Beery curvature is minus imaginary times. So, what you can do is that you can add a resolution operator m here on both sides. So, we will have okay, and again you can use the, for this you can use the Levici beta, and also we, alright. So, I think that is all. Okay. So, then you use the fact that then taking a derivative on both sides, and using chain rule, okay, the same thing. Okay. Now, we do some manipulation, what you will get is, and again multiply by m from both sides. What you will get eventually is which is, so here I am taking from this guy, this is just a number. So, and then this one is I wrote here, and this is the term I will write here. Okay. And then we will only choose for n not equal to m, and you can actually show that for n equal to m term, this one will actually cancel each other about how the energy is changing and with the denominator. Okay, so, once you do that, then the Beery curvature, substituting this in this equation one would get. So, there has to be a cross product. So, let me write it in terms of component. And minus mu and nu are exchanged, or n and m are exchanged, both are equivalent. Okay. All right. So, now we can see that it is nothing but tracking how the Hamiltonian is changing first along some mu direction from some point along mu direction, how the Hamiltonian is changing. Then we are taking an inner product between two states, and then along the perpendicular direction how the nu is changing. So, it is kind of a, and then you are taking the difference with, first you go the nu direction and then you go mu direction. So, it is the curvature. So, curvature, recall, curvature is the failure of the derivative operator between two directions, and here we are taking the different direction. That is the nature of this Beery curvature, that it is an antisymmetric. So, you have to go between different directions, perpendicular direction, and if you go this way versus if you go this way or the reverse way, which we can obtain by the negative sign. So, it sort of measures the amount of flux of this quantity that passes through. This is still not a physical magnetic field or something, but mathematically it is the same thing. It is just how the Hamiltonian is changing. If they do not change, because Hamiltonian itself at different point do not necessarily have to commute. If the Hamiltonian do not commute at different direction, then its change also will not commute, and that is how a curvature will happen. Okay. And Hamiltonian knows what sort of topological space it has. So, it sort of tracks down how the topological space is and how the Hamiltonian is changing, and that will give you the Beery phase. Okay. So, now we have a better understanding of how the state change and the Beery and the Hamiltonian change give rise to a curvature, and we will take this in the next class into block phase in the momentum space and on the Brillouin zone, and then we will take examples. All right. So, thank you very much for your attention. See you in next class.